that. So welcome back and to the topics for this week, which are going to deal with the discussions of second quantization in more detail. And then we are going to start to scratch the surface of Wick's theorem on Friday. So today we are going to refresh some of the things which we did last week. And then we are going to dive into the writing of operators in second quantizations. And then we're going to look at examples. So this is essentially the material this week. I wanted to just bring back some of the things which we did last week. And let me just quickly go back to the slides from last week and have them as a quick reminder of where we were last week. So one of the things which we did was to, instead of now specifying a state with all possible quantum numbers, we are now just going to look at what's called the occupation representation, or the number representation, or what is normally loosely called second quantization. So that means that we're actually making a transformation into a new space where we have transformed away the spatial degrees of freedom, like positions of the particles, and we deal only with the number of particles which occupy a specific state. So you can show mathematically that the Slater determinant in what we normally call first quantization and second quantizations, they are equivalent by a transformation. And what we are going to do now is to label a Slater determinant in this compact way. So keep in mind that when you want to write it out in all its details, these are tensor products or cross products of specific states. So we would have the spin states of a single particle. We would have the spatial degrees of freedom. So this is a very compact representation of a many-body state. And this AS, which we will later drop as long as we deal with fermions. So unless we change the bosons, this AS is something we will drop, but we will keep it in the beginning. And that stands for anti-symmetrized state. So when you see this label, which we later will take away, then that means that we deal essentially with this kind of states. And then when you now look at such a state, we have chosen a specific hierarchy or the way by which we describe the basic state. And then everything else, all the operations we will do will actually be permutations of this basic ordering which we have chosen. So let me quickly bring that back by looking at the whiteboard so that we just remind ourselves quickly of what we did last week and how we defined a specific state here. So let's just do that. So what we did was typically to define a vacuum state. A vacuum state, so this is a state with no particles. And we label that with just 0, like this. And then we had a definition of a specific ordering of the single particle slots which the particles can occupy. So we would have a definition of single particle states or single particle slots, since these are determinants, no, fermions, definition of single particle. So we're going to sloppily call these for single particle states because they refer to the quantum numbers which a single particle can have. And that will also point to spatial degrees of freedom. So what we would have then would be these different slots. And then we would have a slot 1 here, which then would point to a quantum set of quantum number, which we called alpha 1. So this could point to angular momentum. It could point to spin. It could point to other quantum numbers which are needed to define a single particle state. And then this moves up to a state which we call alpha n. So this is the last slot which is being filled by these particles up to a certain level. And this normally for fermions defines what we call the Fermi level. And what you will see often is that we will use a slightly different notation for that. So sometimes we will just call this alpha n equal to F. So that stands for the Fermi level. So we are filling all the states up to a certain level. Then this does not mean that we have exhausted all the possible single particle states, because we have single particle states. If you have a given basis like a harmonic oscillator, you have an infinity of states. So that means that there will be many more here. And this goes in principle up to infinity, but we are typically making a cutoff over dimensionality d. So that defines the number of single particle states, which we use to define an effective Hilbert space. And the level of how we make the truncation is something which introduces an approximation error, because we cannot deal with infinities, as we discussed in the very beginning. And also keep in mind that when we have this compact notation, let's say alpha like this is a tensor product of many components of a wave function. So you could have the spatial part of the wave function, which we label like a phi alpha of x, and this could be given by the spin part, the tensor product with the spin part, where we have s and ms, and more complicated functions depending on the kind of single particle wave functions which we're dealing with. So this kind of notation here, and we should put an alpha prime here. So this alpha contains alpha prime, s, ms, plus all other quantum numbers and states which are used to represent these quantum numbers. So spin and the spatial degrees of freedom, they define different spaces. So the total wave function is then something which we would, for the single particle state, is something which we would compactify in this symbol which you see here. So just keep that in mind, because that means that when we now have two particles, so if we now move on, and if we have two particles, then what we would have would be something like an alpha 1, and then we have the tensor product with a alpha 2 here. But we normally, what we do is that we just sandwich this into an alpha 1, alpha 2. Just to give you an example, if we have two particles, we could have two states. So we could have alpha 1, which is now given, if we write it out explicitly, by this state or this vector. And then we could have an alpha 2, which is given by the same, just to give you an example. And that means that when we take the tensor product of these two states, alpha 2, this is something which becomes equal to 1, 0, 0, 0. And sometimes we can label this as just alpha 1, alpha 2. Sometimes you will see this being labeled as a state 0. So that means you will see sometimes this label as 0, 0. And then if this is something you want to compactify even more, you could label this one as just the first state. So you decide the labeling here. So that's important. So we will always have this kind of compact labeling of different states, as we discussed in the very beginning of the semester. But I wanted to bring this up because when we now go back to the slots which you see here, that means that a given Slater determinant now, an SD, is going to be written out in terms of this alpha 1, alpha 2, up to some alpha n. These are the number of single particle states up to the Fermi level. And this is written like this, AS here. And then we defined this creation and annihilation operators last week. So where we have an A alpha acting on the vacuum state, and that creates a particle in a single particle state alpha. And similarly, we had the rules that if we have A alpha, and this is acting on alpha, this has to be equal to 0 because these are fermions. And we could create the Hermitian conjugate, which is called a annihilation or destruction operator, where we have alpha acting on 0, which is equal to 0. And then we have A alpha acting on a state like this, and that removes a particle. So we're back with the vacuum state, which we have defined here. Later, we will also redefine what we mean by the vacuum state. So I mean, you're free to define it because you will just look at the creation and annihilation operations on a given chosen reference state. So now in the beginning, we are going to think of this as just plain emptiness. So there are no particles, and then we just keep filling particles in the different states. So this is going to give us a compact notation where we now can think of this. If we now look at a specific state, like an example of this alpha 1, alpha 2, the way we are going to order that one is that we have A dagger alpha 1 and A dagger alpha 2 acting on the vacuum state. And we have chosen a specific ordering. So if we go back to the states which we have picked up, so these are the slots of single particle states which forms our basis, and we call that basis the computational basis. So when I say computational basis, these are the states which we use in order to set up single particle states and then many body states. And this just goes in principle up to infinity, but we have a cutoff where we actually stop at level D. And what we have now is that we've filled in this slot and that slot. And we've chosen a hierarchy where this alpha 1 is smaller than alpha 2, smaller than alpha 3, etc. And you could think of alpha 1 just being equal to number 1, alpha 2 number 2, alpha 3 number 3, etc., etc. So you could think of this as slot 1, 2, 3, and then up to a specific value f, which is the same as the number of single particle states you have, and which in this case also becomes equal, or this states up to the Fermi level, and this is now equal in that specific case to the number of particles. But in principle, this little n is supposed to be equal to this d which you have, the total number of available single particle states. But here, we just label this n, little n, which is a number of single particle states, SP state, and we put it equal to the Fermi level. But in principle, little n is not equal to the Fermi level. The Fermi level will then correspond to the number of particles you have, and you keep filling in these different single particle slots. But in this specific case, I've used little n, but in general, little n is going to be equal to this value d, which then corresponds to all the single particle states we have, and d stands for the dimensionality or the length of the single particle states vector. Does that sound okay? So these are again just definitions here. And I will try to be consistent and reserve uppercase letter n for the number of particles which we have. So in this case, we have a two particle state. And then we can, what we did last week was that we found the commutation relation. We found that these operators, A alpha, A beta, dagger, due to the Pauli principle, they have a specific anti-commutation relation which gives exactly equal to 0. And this operator here, A alpha with a dagger or not, that means the Hermitian conjugate, is the same as, let me just reshape that one, of an A alpha of A beta plus A beta here of A alpha. That's the definition of the anti-commutator. And sometimes you will see this with the symbol of A alpha, A beta, but where you put a plus sign to indicate that it's not the same as a normal commutator, which has a minus between the two operators which you have. So this is basically what we did last week, and we went through the demonstration of that relation. So the thing I wanted to bring up now, just by going back to the slides, is the next commutation relation which we need. And that commutation relation is actually A alpha, A beta dagger. And what we need to show is that this is equal to delta, a Kronecker delta or delta alpha beta. So I'm going to go back to the slides for some of the things, because some of the derivations are things which are perhaps not too exciting. And then I want to look at examples on the whiteboard here, because the examples are the things which we will also use in the exercises. So this is the overarching view, is that this is a compact way of representing states, where we now have made a transformation into a new space, which has its name actually. It's called Fock space with an O. Well, that. And this is after a Russian mathematical physicist. And that space means that we have transformed away the spatial degrees of freedom. So let's go back to the slides and parts of the slides from last week. So let's do that. And let's just quickly run through how we can demonstrate the third commutation relations. Because with these commutation relations, we can now start to calculate expectation values and transition probabilities, or what we loosely call matrix elements. So sometimes we often end up to use a very sloppy wording for that. So what we need now is actually, after we have introduced these operators, so this is basically what we did last week, is to look at the relation between A alpha dagger and A beta. So if you now look at the commutation operation here of this specific on this specific state, if now this state alpha is not contained here, then if it's different from alpha, then we know that the action of this A alpha has to be 0, because that state alpha is not contained in here. So that means that this A alpha is just acting on the vacuum state. So then it has to be 0. So that sounds, I guess that sounds pretty plausible. Now, if on the other hand, if this A alpha, as we saw last time, is also, this alpha is not contained here, then this specific state here is actually now given by this A alpha. So it creates a state, alpha here. And then when you take this operator, it destroys it. So that means that first you create a state now here, which has n plus 1 particles, because you add 1. And alpha is not contained in this chain, so you can do that. Note as well that here we have not chosen to reorder the states, because we made this ordering that alpha 1 is less than alpha 2, alpha 3, and we want to keep that kind of ordering. We did not do that here. So we have to be a little bit careful, because that introduces a phase, which we are coming back to. Now, when you do this, what happens now is that you're back to the same state. Now, let's go back to the whiteboard and perform these operations with the state, because now we want to rewrite this in a kind of ordering which we would like to have. So let's just go back to the whiteboard again. So if we look at what we did here, we had a specific state which we acted on with the operators, and that is going to give us a kind of hint of what kind of rule we will have. So we had this specific operator A alpha, and that is acting on this specific state up to an alpha little n here. And in this case which we looked at, then alpha was not contained in the set of states alpha 1, alpha 2, up to alpha n. That means that in the case of this operation here, this gives exactly equal to 0, because there is nothing it can act on. On the other hand, if we just keep the same case, when we looked at this operation here, acting on the same state, alpha 1, alpha 2, of alpha n, what happens then is that we get an A alpha, and then we create a new state alpha, alpha 1, alpha 2, etc., up to an alpha n. And this is now a state which brings us back to the same. When we act with this alpha destruction operator, we take away the particle in state alpha, and then we are just back to the same state here, like this. And that means that if I now subtract these two terms, I'm going to get something which I'm going to base now to build up the commutation relation. But the thing which is a little bit more interesting for us now, if we go back to the slides, I'm just going to switch a little bit back and forth here. The thing which we have to pay a little bit attention to is that when we perform these operations, we actually want now to change this new state which we have created. So if you now assume that the state has been included, so alpha is one of the states here. So that is present. So if it is present, then what we want then, when we perform these operations, is that we want, in order to be able to act with this operator, we have to move this alpha here, k slots. So every time we move it, then we're actually getting a minus sign. Every time we move it, as we defined last week. And that gives us this factor -1 of k. So if you think of this state which you have here, this is just a chain of quantization operators or creation operators. Yeah.
What's the reason that you need to move it?
Because you want to have this state alpha being acting upon that one. Because when you are looking at the states here, this operator has to act on that specific operator. Because when alpha, you have now a chain of operators. So let's go back to the whiteboard here. So you see that a little bit better. So let's redo it. So when you now are, if you just take an example with two states, let's call this alpha 1 and alpha 2 here. This is now written as an A alpha 1 of an A alpha 2. So there is a specific order here, which you have chosen, which means that if we use the commutation rules from last week, this is the same as alpha 2 of A alpha 1, like this. Now, when you now are operating, and this is something which sometimes deceives us, because when we have operators acting on something, it's actually the operator acting on a specific state. Just to remind you, when you have this commutation relation here, you would typically write this as an I times IH, right? Something like that. But what you have performed is to operate on a specific state. And then you use this more compact notation where you take away the specific state you're operating on. So when I'm now going back to this state, which you see here, and I take an operator, so it's always when you see these commutation relations, it's not that they come out of the blue because they have been acting on a specific state, but then you skip the state in the setup of the commutation relation. So when you have, let's say, I don't know if you remember from basic quantum mechanics, you could have something like Jx and Jy. To get the commutation relations, what you're actually implicitly doing is that you have Jx, Jy acting on a specific state minus Jy, Jx acting on the same state. And then you find what that gives you. But when you set up the commutation relation, you skip this specific state psi. So these operators are always acting on something. So that means that when you now look at this notation here, alpha, this is the same as A alpha dagger having acted on 0. So that means that when I now have an A alpha dagger, A alpha, acting on this specific state, alpha 1, alpha 2, what we need to do then is actually, if alpha is contained in this set, alpha 1 and alpha 2, suppose alpha now is equal to alpha 2, what I'm having now is that I have A alpha 2 dagger of A alpha 2 acting on A alpha 1 dagger of A alpha 2 dagger acting on the state 0. Now, remember again that these are tensor products of states. So each one of them has actually acted on zero. So when I now want to see what this gives me, I need now to change this to minus, and then I have an A alpha 2 dagger, A alpha 2 dagger, and then I have an A alpha, sorry, no, I was a little bit too fast here. I have an A, I make a change, I have an A alpha 2 here, and then I have an A alpha 2 dagger, and then I have an A alpha 1 acting on zero. Now, the kind of notation here means that alpha 1 acts on zero and creates a state alpha 1, but it means also later that alpha 2 also acts on zero. So it's not only alpha 1 acting on zero, but also alpha 2. If I want now to perform the operation with alpha 2 here, so this state here, what I've done now is actually to rewrite my Slater determinant in the following way. So this is the same as minus A alpha 2 of A alpha 2 acting on alpha 2 and alpha 1. So now this we can take this operation, and I remove a particle in alpha 2. So this gives me a minus sign here, as you can see. And that minus sign means that now when I have done this reordering, I get a state. If we now move to the next page. So what we have now is the following. We have minus A alpha 2 dagger. And then I have taken away alpha 2 here, and I have alpha 1. So I have multiplied this with A alpha 1 dagger acting on 0. This is now the same as minus alpha 2, alpha 1 in this compact notation. Now, I don't want this ordering because I have made an ordering. And my ordering says now that it has to be equal to alpha 1, alpha 2 here. That's the ordering I have opted for. So that means that what I would do then is actually to rewrite this one, this state which you see here, which is minus A alpha 2 dagger, A alpha 1. And then I use the commutation rules, which we defined last week. So we have A alpha 2 here and A alpha 1 dagger. We know that this is 0. So that means that this equation which we have here, that becomes equal to, let me just rewrite it a little bit better. This gives us A alpha 1 dagger, A alpha 2 dagger acting on 0. And that's the same as A alpha 1, A alpha, no, alpha 1. Now me messing up things here. Too many symbols. This becomes alpha 1 and alpha 2 here. So everything is just us introducing a compact notation, but when we have this compact notation, we have to develop the rules of the game. So we want this specific ordering because that's the one we will use to define all operations on. Now, when we have an operation of the type which you see here, this one, with that operator, which acts on this state, we now need to bring this operator here, which now has created a particle in the state alpha 1, alpha 2, we need to bring that together with the creation operator because these are acting on the vacuum state. And when we do that, then we know that this one takes away a state here in alpha 2, and then this one creates it back again. But then we have a new ordering where we have interchanged alpha 1 and alpha 2. And then we have decided that we want to have a specific ordering where alpha 1 comes before alpha 2. And then we have to bring in a phase factor. Does it sound okay? So this is just because we now want to use the fermion rules in order to define the states, and the operations which we're going to do now have to reflect the anti-symmetry which fermions have to obey. So if we then go back to the slides, and let's do that. So this is still some of the material from last week. And so what we have then is now, if we take these two relations here and we just add them, we see now that the first state which we have here, if alpha is contained, just gives the same state back again. And if I act with this one on a state alpha, which is already occupied, this is 0. If I add these two equations, I can then define this anti-commutation relation with the same state in the creation operator and the same state in the annihilation operator. So that's the case if the two states are the same. And then we need to look at the case where we don't have alpha equal to beta, but we have alpha and beta being different. So we could then have a state, if we now look at the case which we have here, if we have alpha beta here, then if I look at this one, this would take away a state beta. But then when I have alpha here, I'm trying to create a state alpha. So that has to be 0. So in this case, I have a n minus 2 particles here, and then I add 2. So if alpha and beta are contained, we know that this has to give 0. So that's one of the relations which we need. And the same happens here. If alpha is contained here and we have this operation, this also gives 0. Now then we have to look at the case where, so we are looking at the cases where we can contain both alpha and beta, and then either alpha or beta, and finally none of them. So we have to look at all the special cases which can arise when we act with this operator here on a given state. So keep in mind that when we're looking at these operators, they're always acting on something. And in this specific case, when it's different from alpha, then clearly this is a possibility. So this creates a state, so it takes away beta, and it adds a state alpha. So in this particular case, alpha is not contained, and you would get a similar case when you have beta and alpha is contained. And then if you look at this case, what you have then is the operation of alpha, where we now interchange, we create a state alpha, and then we need now to interchange alpha and beta, so we get a minus sign here. Then finally, if the state vector does not contain alpha and beta, what we are getting now is that in this specific case, we are trying to destroy something which doesn't exist. So that has to give us 0. In this other case here, we are trying to create a state alpha, which already exists. So this is different. And then we are trying to destroy a state beta, which is not included. So that gives us also 0. So if you summarize all these three cases, which you see here, so the first case here, the second one, and then we use this particular result here as well, then you can summarize everything to this specific commutation rule. And that is the third commutation rules, which we actually need in order to deal with fermions. So that means that what we had last week is the definition of a creation operator. We have the definition of the annihilation operator. And then we have the three anti-commutation rules. And this is the thing which we roughly ended with last week, except for the part that we didn't show the final anti-commutation rule. So what I want to do now is actually to look at some examples and how we can use these rules to calculate expectation values. So it's often better to actually look at specific examples after we have defined these anti-commutation relations. So let's go back to the whiteboard and look at examples for the rest of this lecture and also in the beginning of next lecture, so that we can practice a little bit. And one of the exercises this week actually deals with us practicing with these relations. So one of the cases we are going to look at now is to calculate the inner product of a two-body state. And I also wanted to say one thing here is that everything I do now is to prepare you for Wick's theorem. Because when you're going to see what I'm doing now, this is going to be boring and it's going to be full of possibilities of making errors because we are using these anti-commutation rules. Wick's theorem simplifies all these calculations. So, but now we're just going to go step by step because this will motivate the introduction of Wick's theorem, and you will see why Wick's theorem follows from many of these calculations. So let's look at an example where we calculate the norm of a two-body state. So what we are having now is a state alpha 1 and alpha 2, and we want to calculate the inner product of this state here. So if these are normalized, this should be equal to 1. That's ideally that's what we want to show now. So let's write it out and then try to develop the strategy which will then show us how we can reach Wick's theorem and how we can use Wick's theorem to simplify these calculations here. So what we need then is to calculate this quantity here. So we will have an A alpha 2, an A alpha 1, and then I have an A alpha 1 dagger, and then I have an A alpha 2 dagger acting on 0. So this is the norm in second quantization. And we have skipped the spatial degrees of freedom, which means that we are in a way taking away the part of the norm which involves an integral over the spatial degrees of freedom and perhaps a sum of a spin degrees of freedom, etc., because everything is now contained in this occupation of the states. So the question now is, which strategy should we apply? So what we have is that A alpha acting on 0 is equal to 0. And if I have an A alpha acting on the vacuum state, this is the same as us creating a particle in the state alpha. And that is normally assumed to be different from 0. So one thing you can see now is that a brute force way of approaching this problem is to use the anti-commutation rules and simply change the order of these operators so that we have an annihilation operator acting on a vacuum state. And this is something which, when you see this rewriting, these are going to be terms which you will use also in the definition of Wick's theorem. So we're going to show first Wick's theorem with up to 4 operators, and then by induction, you can prove it for as many operators as you want. And when you have Wick's theorem, you can really simplify the calculation of these kind of expectation values or quantities we want to calculate, like the norm or whatever. So let's now do this in a very, less friendly and not so smart way. So what I'm going to do now is simply to change alpha 1, the destruction operator, annihilation operator, and have that moving to the right. So we would have this one, and now we interchange this operator alpha 1 with alpha 1 dagger. So what I'm going to get then is obviously a delta alpha 1 minus A alpha 1 dagger A alpha 1, like this. And this now contains A alpha 2 dagger acting on the vacuum state, like this. So the only thing I used now was actually the anti-commutation rule. So then we know that if we look at the first term, if we take that, so the first term is simply going to give us a delta alpha 1, which is okay. That's different from 0, that's 1. And then I have an expectation value now of A alpha 2 of A alpha 2 dagger acting on 0. And clearly in that case, this term which you see here is also equal to delta alpha 2 of alpha 2. Because if you, it has to be that, but you can show that with the anti-commutation rules. So let's just take this piece here. So you would have 0, and you can rewrite this one as a delta alpha 2, the Kronecker delta, minus A alpha 2 dagger, alpha 2, acting on 0. And now you see that the last term gives automatically 0, because you have this alpha 2 operator acting on 0, and that's by definition 0. So the first term gives us 2 Kronecker deltas. And this is actually the result we want, right? Because we're assuming that these states are normalized, so that when we take the norm, that should give us the Kronecker deltas of alpha 1s and alpha 2s. So this is essentially what we want, but then we have the rest, which we have to show is equal to 0. So that's what we're going to do now. So this was a small intermediate step. So let's just leave that as an intermediate step for that piece. So you see the kind of action which we do now is that we want to transfer the annihilation operators to the right so that they can act on vacuum and they give us automatically 0. Now, just as an intermediate thing, before we move on, this ordering, which you see here, with the destruction to the right and creation to the left, that is called a normal ordered product. And that's going to be used in the definition of Wick's theorem. So Wick's theorem is actually going to give us a chain of operators within an expectation value, which can be rewritten in terms of what we call normal ordered chains of operators. So we have ordered the operators, so all the creation operators are to the left and the annihilation to the left, not to the right, which means that they act immediately on a vacuum state and give us automatically 0. So this term here gives us automatically 0 because we're just acting on vacuum with a destruction operator. But then we have a new term here, which we need to pay attention to. So we have a minus, and then we have 0, and then I have an A alpha 2 here. I have an A alpha 1 dagger, and then I have an A alpha 1, and then an A alpha 2 dagger, 0. And now you see the pattern here, because what I want to do next is simply to interchange these operators here. And if I do that, then I have immediately a state with the A alpha 1, which acts on a vacuum state, which then is not filled with alpha 1, so that gives automatically 0. So let's look at the last term here before we take a small break. So the last term which we get, so the first term is just a Kronecker delta. So the last term here, that gives us a minus, and then we have a 0, and we have an A alpha 2. And then we have this, if we go back here, we have an alpha 1, and then we have the, so let's just write this, not that, but an alpha 1 dagger. And then we use now for the last one here with the interchange of two operators. So we get a Kronecker delta, which says that we have a delta alpha 1, alpha 2, minus an A alpha 2 dagger, A alpha 1, acting on the vacuum state. So what should this give us? So alpha 1 and alpha 2 have to be different. So what should we get from this expression here? Exactly, because you see now that this term here, this destruction operator acts on the vacuum, and that gives us 0. Now, we have assumed that alpha 1 and alpha 2 are different from each other, because else we would have to deal with bosons. Because with fermions, you cannot have more than one particle in one single particle slot. So this also has to be, this term here also has to be equal to 0. So the last term is actually equal to 0. So what survives then is what we expected. So we would have an alpha 1, alpha, or rather let's write it in a more compact way. So if we look at this norm, which we calculated, alpha 1, alpha 2 here, this is equal to delta alpha 1, alpha 2, and delta alpha 2, alpha 2 here. And that is different from 0. Oh, sorry, it should be 1, yeah, sorry, yeah. So in this case, we have used the second quantization formulas to calculate a specific norm. So what we're going to do next, after the break, is to look at more examples. And we are going to define some specific operators. And we're also going to show how we can rewrite the Hamiltonian in terms of a second quantization formalism. And then we're going to use that to calculate expectation values, still using this kind of brute force approach. So everything I'm going to do today is going to serve as a motivation for Wick's theorem. Because when you're getting many single particle states, this is not going to be an exciting exercise. And you can see that if you do this by hand, this is very error prone. Because if you have, suppose now 4 states, you would have an alpha 1, alpha 2, alpha 3, and alpha 4. And that means that after some time, you get lost in all these applications of the anti-commutation rules. So you can systematize this, and Wick's theorem is the way you systematize it. And that's what we will be deriving tomorrow and prove tomorrow as well. Should we take a small break? Is that okay with everybody? So let's do that. I'm going to put the recording to pause. Okay, so what we're going to spend some time on now is to calculate some specific expectation values. And what we are going to do now is to look at specific operators. So the next example is us defining an operator which we're going to see quite often. So this will be an example 2 here. And now we define something which we are going to call a number operator. So n with a hat is a hat over means that this is an operator. And this is going to be a sum over specific single particle states of A alpha dagger of A alpha. So this is normally called a number operator, and you will see immediately why this is a number operator. So one thing which is important to note as well is that this operator is actually idempotent, so that means that it's equal to itself. And we are going to look at an example here pretty soon, but let's look at some basic operations with this operator. So what happens when I take one of these states, A alpha dagger of A alpha, and that acts on a specific state up to alpha n. And we're assuming now that we can actually have 2 cases here. So we have 0 if alpha is not contained in this set of states of alpha 1, alpha 2 up to alpha n. And we see that immediately because if it's not contained, this is an operator which will simply now, when we act with A alpha, and if it's not contained, it's just going to give us 0 because you have alpha, A alpha acting on a vacuum state, and that's a 0. And then if it's not contained in the state, then this is going to be equal to, if we take it away, then it's going to give us a state, A alpha, so we can just rewrite this as alpha 1, alpha 2 up to alpha n, if alpha is contained in this set of states, alpha 1, alpha n here. Because that means that if we now take A alpha acting on that specific state, alpha 1, alpha 2, and then we go up to some alpha k, and there is a state alpha here, and then we have alpha k plus 1, and this continues all the way up to alpha n. This is then equal to A alpha multiplied with A alpha dagger, and then we have made these permutations k times. And then we have the chain of A alpha 1, A alpha 2, up to A alpha K. And then I have these are the operators, A dagger, and then I have a K plus 1 up to A alpha N dagger acting on the vacuum state. So I have now, when I do this operation here, I've actually performed an operation where I now, oh, sorry, I wrote this one. This is not correct, what I have here. So what I would get is an A alpha dagger, A alpha, and then I have an A alpha. I forgot to put in that one because what I did was to keep this one, and then I interchanged all the operators here by moving this A alpha dagger K times. So that gives me a phase factor. Now what happens next now is that this one, when that acts on a vacuum state, it just creates the state alpha, it takes it away, and then it moves it back again. So this is going to give us a minus K, and then I have an A alpha dagger, and then I have an A alpha 1 dagger, A alpha 2 dagger, and then up to this A alpha K dagger, and A alpha K plus 1 dagger, and this goes up to the final one. And then I move this alpha here back to the slot where it was, and then I have to make K interchanges of creation operators. And when I've done that, then I'm back to the same state as we put here, as we set up here. So this actually gives us back the same state. If you then act on a specific state with a sum over all these creation and annihilation operators, so if I now take this operator N and act on a state alpha 1, alpha 2 up to alpha N, and my summation here N runs from alpha equal to alpha 1 up to alpha N. So if I'm running through all these states, so then I have an A alpha dagger, A alpha. What you see now is that every time this acts on a specific state, I just get the state back again. So when I have this sum here over alpha equal to alpha 1 of alpha N of A alpha, this acts on a state alpha 1, alpha 2 up to alpha N. So if the state, I'm now putting up an explicit sign from alpha 1 up to alpha N, but I could actually let it move higher up. But if it moves beyond alpha N, it's just going to give us 0. So every time this operator here acts on the Slater determinant, we just give the state back. And I'm doing this n times. So I'm doing this alpha n times. So this is simply going to give us n times the Slater determinant, alpha 1, alpha 2, up to alpha n here. And that n is the number of particles which I have. Because every time I act with this operator here, or this operator, I just produce the same state, and I do that n times. So that gives me the number of particles which I have present. So then you see that if I now calculate the expectation value between alpha 1, alpha 2, the same state, alpha n of this operator here, alpha 1, alpha 2 to alpha n, this is simply going to give us n, which in our case is a number of particles. So let's also show that this operator is actually something which we call idempotent. So we're just going to look at the operator itself. So let's change page. So if we now look at this operator, if we now pick a specific state, Ni, for this operator, that is going to be given by AI dagger of AI. If I now square this operator, if I take Ni squared, that is going to be AI dagger times AI multiplied with AI dagger AI, like that. Now, when we are looking at these kind of operations, they're always acting on some specific state. So this N acts on something, but we are suppressing that. So what I'm going to do now is to rewrite these two operators, this creation and annihilation operators. I'm just going to rewrite them using the anti-commutation rules. So I can rewrite this now in terms of an AI dagger, and then I have 1 minus AI dagger, and then I have AI, and this is multiplied with AI here. Now, when you now look at it, this is going to be given by AI multiplied with AI. So the Kronecker delta here is equal to 1 because I have delta, the Kronecker delta of I and I. And then I have minus, and then I have AI dagger, and then I have AI. And if we now operate with this one on a specific state, so if you think of this acting now on AI of AI, acting on, so if we take this of AI dagger, AI, and this acts on a specific state, which we now could call a state I. Then where I is one of the possible particles which are in there, then the last term is going to give us 0. And the only term which is going to survive here is actually this first term here. Because if it acts on a state with I, then I'm destroying the state with I, but then I'm trying to destroy a state with I, which is no longer there. So when this one acts on I, this simply gives us 0. But then I have AI here again, which is acting on 0. So that also gives me 0. So that means that this is just equal to AI dagger AI. So when you look at these operators, we often suppress the fact that they do actually act on a state. So you would write it in this more compact way, where you write Ni squared is equal to Ni. So that means that Ni squared is equal to Ni. And you can then move this to the general case, which means that N squared is equal to N. So that's just one of the properties of that specific operator here. Now, there are some other properties which are also useful, but I will leave them as a small exercise for you guys. So one thing you can show is actually that if I take the commutation relation between Ni and Nj, this is equal to 0. You can also, if you take now a commutation relation between the operator AI of an Nj, a state like that, that is going to be equal to I, the overlap with J, multiplied with AI. If I take the, and I haven't specified this overlap, so if you assume that these are orthogonal states, then I overlap with J should be equal to 0. If they're not orthogonal states, then it may be different from 0. And then I have another relation here. So I just invite you to play around a little bit with it. And you can show that this is equal to minus Ij of I. So this is a case where you require, obviously, that if you have an orthogonal basis, that I has to be equal to J. That's the only case which can lead to something which is different from 0. So this case here is actually, in most case applications which we're looking at, is given by Kronecker delta. So I just invite you to take a look at these relations here, and then we are going to use this a little bit later. But one of the things I wanted to move on to now is a new example, And I'm going to show you later what the expressions for a operator in second quantization is for one body operator and two body operators. So now I'm just going to state what it's going to look like. And then later I will show you how you can derive that specific expression. So what I'm going to say now is that the operator for H0, which we defined in the beginning of the semester, which was given by the sum over one body operators in first quantization. So this is I equal 1 up to the number of particles. And this H0 of x of I, that is normally given by kinetic energy. So you would have something like this. And then you have the second derivative. And then there can be some external potential like a harmonic oscillator or other relevant potentials which are included to define the one body part of the operator. And that's the piece which we discussed the previous week and the week before. So what I'm going to state now is the expression for this operator in second quantization. And then later I will derive the expression. But now we're going to calculate expectation values with that expression. So what we are going to show a little bit later is that in second quantization or in the number representation, in second quantization, you can rewrite this operator as an H0 with a sum over states alpha and beta. And then we have an expectation value or an integral here. It's actually an integral over H0 with a state beta. And then I have an A alpha, A beta. And if we have assumed that beta and alpha are eigenstates of H0, then this reduces to a single sum. So this will be the general expression. And I'm going to show this later, how you can derive this expression from the expression in first quantization, the standard one which we had here. So this is the expression which you have seen till now. So the question is, how do we go from here to here? So let us assume that we have this expression and then we derive it a little bit later, because now I just wanted to practice a little bit with second quantization. So one assumption in the calculations here we are going to make now is that we have a simpler case. So we're going to assume now that alpha of H0 of beta, which we defined as an integral over x, over the domain of variables which we have a d of x, a phi, alpha of x, and then we have this operator of beta and then beta of x. We are going now to assume that H0 acting on this phi of beta of x is given by some epsilon beta times this phi of beta. And we write this in a more compact way as this state beta, and that's given by beta here and that state. This is a more compact notation which we have been using. So that means that if I take this, calculate this integral between these two states, this has to be equal to delta alpha beta times epsilon alpha. In this specific case, if I have assumed that this basis, alpha and beta, is an eigenbasis of H0, then my operator H0 simplifies to just a sum over one of the variables, alpha and beta. So we get then a sum over alpha, and these are all the possible states which the system can access. And I would have an epsilon alpha multiplied with A alpha dagger, A alpha. So it looks like almost like the number operator. So let's assume now that we have a two-particle state, two particles. And we define a state alpha 1 and alpha 2 here. So that is the same as A alpha 1, A alpha 2 dagger acting on the vacuum state. Now, you remember that when we did this calculation in first quantization, as we loosely called it, when we calculated the expectation value of this state, alpha 1, alpha 2 of H0, alpha 1, so we did this the previous week and the week before, then this was simply equal to epsilon alpha 1 plus epsilon alpha 2 here. So let's see now that we get this expression. And let's do that in second quantization. So as I said, everything we are doing here is a way to motivate the introduction of a simpler recipe, which in our case is going to be given by Wick's theorem. But now we do this in a very brute force way. So let's now calculate. So we have a sum over alpha. We have a state alpha 1. So we have an A alpha 1, A alpha 2. Actually, it's alpha 2 here because we're taking the transpose. And then we have this element, epsilon alpha, of A alpha dagger, A alpha. And this is multiplied with alpha 1 dagger of alpha 2 dagger. And then we have 0. So this is the expectation value which we need to look at now in second quantization. So you see quickly now that we have three creation operators and three annihilation operators. And this is going to be a boring exercise of us moving around with the contraction rules. And it's going to serve, as I said, as a kind of motivation for introducing Wick's theorem. So let's now do it. And the thing we need to look at is not the sum, but we can just stay with the expectation value of A alpha 2, A alpha 1, and then we have A alpha, and then A alpha 1 dagger, and A alpha 2 dagger, acting on 0. So the first thing we're going to do now is try to shift this operator A alpha to the right here so they can act on a vacuum state. And then we will get 0. So with this set of operations, what we're going to get now, when we start preparing it, so this is going to be, and I will skip 0 in the notation here. So we'll just look at the creation and annihilation operators. So that means that I can now rewrite this expression, A alpha 2, A alpha 1, and then A alpha dagger, and I can rewrite this as a delta alpha 1 alpha minus, and then I have an A alpha 1 of A alpha, and this is now acting on A alpha 2 dagger, like that. Does that sound okay? Now, what I do next is I keep manipulating the second term. So what I'm going to get now is that this is going to look like as follows. So I will have an expectation value of A alpha 2 of A alpha 1. And now in my case, what happens is that alpha is equal to alpha 1. So I'm going to get A alpha 1 here. So when you look at this expression, I have the Kronecker delta, which simply gives me that alpha is equal to alpha 1. And then I have an A alpha 2 dagger. That's the first term. So I have the Kronecker delta. And then the next term gives me simply this A alpha 2, A alpha 1, A alpha dagger. And then you have an A alpha 1 dagger, A alpha, and then an A alpha 2 dagger. So now I'm going to leave the first term, and I'm just going to manipulate with the second term so that I can actually rewrite that one as a set of operators with the creation operator to the right and the rest to the left. So if you look at the second term, what I'm going to get now, if you take this term here, So you can actually now, since alpha 1 and alpha 2 are different as well. So one of the things which we will be doing, if you look at the first term, I will have an A alpha 2, and then I have a 1 minus A alpha 1 dagger, and then I have an multiplied with an alpha 1. No, sorry. So I have an A alpha dagger, and then I have an alpha A alpha 1 multiplied with an A alpha 2 dagger, like this. And again, alpha 1, we just have to keep in mind also that alpha 1 is different from alpha 2 here. So I can, if I look at the first term, I can also rewrite that one in terms of a commutation relation with alpha 2 here. I can do the same thing with this one. So if you look at the first term here, this A alpha 2 with an A alpha 2 here, that is something which I can rewrite in terms of a Kronecker delta of alpha 1 and alpha 2 here. But let's now try to rewrite these terms slowly. So we have the first term, which I now rewrote like this. And then if I take the last term, so we have the first term, and then the next one, and then I have a minus. So minus A alpha 2 of A alpha 1, and then I have an A alpha dagger, and then I have an A alpha 1 dagger, and then I'm going to get a Kronecker delta between alpha and alpha 2. So I'm going to have a delta alpha of alpha 2 here, and then I'm going to get the next term, which is going to be, so if we do that properly, I have an alpha 2 and then minus, and then I have now an A alpha 2 dagger, A alpha, acting on the vacuum state. So this is something which will act on the vacuum state, but we have suppressed the fact that it acts on the vacuum state. So what you get then for the last term here, since this will act on the vacuum state, that will be 0. So you see that? The way you actually do this manually now, in a not very exciting way, is that every time we have such an expression, we try to shift the operators so that we have at least one annihilation operator which acts on the vacuum state. So here, what I did now was to take this term which you see here and just rewrite it using the anti-commutation rules. And then I got the annihilation operator A alpha acting on a vacuum state, and that gives me 0. But now you see that what I'm having is actually this operator here, where alpha is equal to alpha 2. And then I would have to rewrite that one as well. So if you look at this term, what I have done now, I have a Kronecker delta. So this term gives 0. I have a chain of operators here as well, which I need to take care of. And then I have this operator here, where now alpha is equal to alpha 2. So I can then rewrite this operator here in terms of alpha 2. So you see now that this one, and let's just sneak in some space in here. So this one reduces to minus A alpha 2, A alpha 1, A alpha 2 dagger of A alpha 1 dagger, like that. And then what we have next, the other term which we need to take care of is actually this term, which you also see here, where we have an A alpha 2 and A alpha 1 here, and we have alpha 1 and alpha 1 here. So that term actually was something which I think I wrote it wrongly here. Let me, because that comes from this. Yeah, it should be alpha 2 on the last one. So this one is actually a number 2 here. So what you see now, if you look at these terms which we have, they are not that different. So the first term has a Kronecker delta, which says a delta alpha 1, which we have here. So this Kronecker delta just gave us this 1 here, which I replaced here. And then when we manipulate these expressions, we are going to get, if we now continue, so let's do that. So let's write down, and now I need to remind myself of what it looks like. So we have that one. So if we take the first term, we have an A alpha 2, and we have 1 minus, and then we have an A alpha, and this is given by an A alpha 1 of an A alpha 1 acting on an A alpha 2 dagger here. So what we're going to do now is simply to keep rewriting things, and you can see now the first term gives us A alpha 2 alpha. Now it's me who I get an A alpha 2 A alpha 2 dagger minus, and then I have an A alpha 2 of an A alpha 1, and then an A alpha 1 and an alpha 2 dagger. So the first term had already a Kronecker delta with alpha 1. So this has a delta alpha 1 of alpha 2 here. So if we take the first term, we can rewrite that one as a delta alpha 1 of alpha 2. And then I have a delta, no, alpha 1. And then I have a delta, this is 1, a delta alpha 2 minus an A alpha 2 here, and then A alpha 1, alpha 2. So that's the first term here. And when that acts on the vacuum state, the last term here, that gives us 0. So this term is going to give us a delta alpha 1, alpha 2, and then I have a delta alpha 2 of alpha 2, but with the constraint that we had delta alpha equal to alpha 1. So that will give us a specific term now, which is going to give us simply this energy, epsilon alpha 1. That is that term. So when we go back to the expression here, one of these terms gives us the epsilon alpha 1 term. Then what we need to do next is actually to elaborate all these other terms. And when we've gone through all these changes, which are not very exciting, we are going to get a final term. So finally, we will also get, also a term, after all this manipulation, a term which goes like epsilon alpha 2 here. So you see now that the reason why I want to bring this up is that this is not a very good way of doing it. So I mentioned last week that by introducing second quantization, we are going to simplify the calculations. But when you look at what I'm doing now, it doesn't look like a simplification, right? This is something where you can actually get lost in the jungle of all these sub-indices. Now, what this is doing actually is to motivate the introduction of Wick's theorem. So I just wanted to bring up this example, which you will also do in the exercises tomorrow. And you will see that this is not a very nice way of calculating things, because if you have more than 2 particles, you are going to simply get lost in the wood of all these subscripts. So this calculation, which I've introduced here, is something which motivates the introduction of Wick's theorem. So if we then move on a little bit, so this is this motivates, as I said, some simplifications. The introduction of Wick's theorem. And in order to do so, we need to introduce some definitions of Wick's theorem. And in order to do so, we need some definitions. So one thing is that when we now look at an expectation value of this A alpha, A beta dagger of 0, when we now use the anti-commutation rules, what this becomes equal to is a Kronecker delta of delta alpha beta 0, and then we have minus, and then we have 0, and then an A of beta of A of alpha acting on 0. Okay, this is just using the anti-commutation rules. Normally we skip the 0 and we write this in a more compact way. But let's wait a little bit with that. So what we have is that this expectation value, which we looked at first, A alpha, A beta of 0, this is something which becomes equal to alpha or beta. And that's where we have the Kronecker delta, delta alpha beta. This kind of expression is something which we would rewrite in terms of a specific symbol. So I'm going to rewrite this now, this expression which we put up, in terms of an A alpha, A beta dagger, and I'm going to put a symbol on top of it, and I'm going to call this a contraction. So I'm contracting operators. And then I'm now going to put in a sign here where I say plus, but then I need to be a little bit careful. So I'm going to call this a normal order product. So this is a normal order product of a chain of operators, A beta and A alpha. So what does normal ordering mean? So this N is not the number of particles, but it stands for a normal ordered operator. So normal ordering means that all the creation operators are to the left and the annihilation operators to the right. So this term here, a normal ordered chain of operators, is actually equal to 0. Because this term which you have here, this specific term, this one, has to be equal to 0. So if you can rewrite a set of operators in terms of a normal order product, you don't need to run any calculations because that's immediately equal to 0. So these are just definitions which we are going to use now. So if we look at this specific case, what we had, so the original operator which we had was this operator here. Now the normal ordering has a sign which depends on the number of times we have to change the order of the operators. So in our case, the number of times we needed to change it was actually 1, because our original operator was given like this. So then we had to change A alpha and A beta once, and that gives a minus sign. But what you see here are actually definitions of what we are going to use to define Wick's theorem. And that will allow us to simplify the calculation of that set of expectation values which we looked at now. So this quantity which you see here, this one, is now the same as this one, but where we started with the original operator here. Now, these are quantities which we will define tomorrow in a better way, but they will serve as a kind of compact way to represent a specific expectation value. And Wick's theorem will be formulated in terms of these contractions and normal order products of operators. But we will discuss that in more detail tomorrow, in the lecture tomorrow. And you will see then that when you then go back to the calculations we did here, and we didn't even complete them, and the reason why we didn't complete them fully is simply because this becomes a boring exercise. And you don't get many new insights in with it. And with Wick's theorem, you can actually simplify this calculation immediately. And we will see that tomorrow. Okay, we're going to stop here. And then tomorrow we will discuss Wick's theorem in more detail.